This presentation is part of the TI-Nfocus AP Calculus video series. In this video, I'll discuss a specific concept associated with the 2018 AP Calculus exam, free response question BC2, namely arc length and parametric equations. My name is Steve Kokoska. I'm a professor at Bloomsburg University in Pennsylvania, and I'm a former AP Calculus chief reader. Here's an outline of the information presented in this video. I'll start with a little bit of background information about parametric equations. And then I'll talk about trying to measure the length of an arc or path. And that is, can we actually measure a piece of a curve defined by parametric equations? I'll derive a formula for the length of a curve C, connect this expression to particle motion, and leave a few examples for you to try. Let's suppose a particle moves along the curve C, as shown in this figure. Now, we can't describe the curve C by an equation of the form y equal f of x, because the curve C fails the vertical line test. But we can think of the x and y coordinates of the particle as functions of a third variable t, often corresponding to time. Therefore, we can write x equal f of t and y equal g of t. And this pair of equations is often a very convenient way to describe a curve. And it suggests the following definition. Suppose x and y are both functions of a third variable t called a parameter, by x equal f of t and y equal g of t, called parametric equations. For each value of t, we can find the point x equal f of t, y equal g of t, which we can plot in the coordinate plane. As t varies, the point xy also varies and traces out a curve C. The curve C is called a parametric curve. The parameter t does not necessarily have to represent time. In fact, we could use any letter for the parameter. However, in many applications of parametric curves, t does indeed denote time. And in these cases, we can interpret the point xy as the position of the particle at time t. Let's try an example. Suppose we want to sketch the curve defined by these parametric equations over the interval minus pi to pi. Now, each value of t in this interval produces a point on the curve. So, we could construct a table of values. That is, select some values of t, find each corresponding point xy, plot these points, and then connect them with a smooth curve. Now, the process isn't hard, but it can be a little long, tedious, and inaccurate. Technology is a huge help here. Using the TI-Nspire, I can simply define the parametric equations and plot the curve for t in the appropriate interval. And I can also trace along this curve. The value of t and the corresponding point xy are given on the screen. And if this is in the context of particle motion, I can actually visualize the direction of motion of the particle along the curve. So, what about arc length? At first glance, it might not seem possible to determine the length of a curve over an interval. I mean, after all, we're trying to measure a possibly complicated curve, not a straight line. So this example is meant to give us some hope that we can indeed measure the length of a curve. Let's suppose that a particle moves about in the plane so that its position is given by these parametric equations. Find the length of the path of the particle. First note that the domain here is t between 0 and 56. And here's a sketch of the curve represented by the parametric equations. It certainly looks like part of a circle. Let's try to eliminate the variable t to see if we can identify the graph of this equation in terms of only x and y. So consider the expression x squared plus y squared, Using the expressions for x and y, we can indeed eliminate the variable t. And this confirms that the path of the particle is along the circle centered at the origin with radius square root of 56. So the length of the path is 1/4 the total circumference, or 1/4 times 2 pi r. And that simplifies to pi times the square root of 14. So this gives us some hope that we can find the length of a more general curve described by parametric equations. One method to obtain a general formula for arc length of a curve described by parametric equations is to recall the expression for arc length of the graph of a function y equal f of x. If f prime of x is continuous, then the length of the curve is given by this expression. Suppose, however, that the curve is defined by parametric equations. The assumption here about f prime of t means that the curve c is traversed once, from left to right, as t increases from alpha to beta. Use the expression for dy dx and the substitution rule to obtain this expression. Since dx dt is greater than 0, we can rewrite the expression in this form. Even if the curve cannot be written as y equal f of x, the equation for arc length on the previous slide is still valid. We can obtain the same result using straight line approximations. And I really like this derivation process because there are some very nice calculus concepts involved. Divide the interval alpha to beta into n equal subintervals of width delta t. Let t0, t sub 1, all the way down to t sub n be the endpoints of the subintervals. Then x equal f of t sub I and y equal g of t sub I are the coordinates of the points p sub I that lie on C. The polygonal path with vertices p0, p1 down to p sub n approximates the curve C, as shown in the figure. And since we can find the straight line distance between 2 points, we can now find an approximation to the length of the curve. It seems reasonable that the length L of the curve C is the limit of straight line distances. We can take more and more points on the curve C, and our approximation gets better and better. If we apply the mean value theorem to f on the interval t sub I minus 1 to t sub I, there exists a number t sub I star such that this is true. Now let's define delta x sub I and delta y sub I. Then the result from the mean value theorem can be written in this form. Similarly, we can apply the mean value theorem to g on the same interval. And there exists another number, t sub I double star, such that this is true. Let's put all of this together. The straight line distance between p sub I minus 1 and p sub I is this. Using the expressions for delta x sub I and delta y sub I, we have this expression. And a little simplification yields this. So the length of the curve is this limit, and this is almost a Riemann sum. It's not exactly because t sub I star is not equal to t sub I double star in general. However, if f prime and g prime are continuous, it can be shown that this limit is the same as if t sub I star equals t sub I double star. Therefore, the length of the curve C is given by this integral expression. And here's another way to write this using Leibniz notation, which is the same result we obtained by transforming the original expression for arc length. I feel obligated to state this result more formally as a theorem. So here's the arc length formula with all the appropriate assumptions. And let's connect this result formally to particle motion. Suppose a particle moves along a curve so that its position vector at time t is given by r of t. The velocity vector v of t is given by this expression. And the total distance traveled by the particle from time t equal alpha to time t equal beta is given by the integral expression that we just derived. And finally, here are a couple of problems for you to consider. Graph the curve described by the parametric equations using technology, and find the length of the curve, also using technology. I hope this video provides some insight into arc length and parametric equations, a few AP Calculus type problems, and the use of technology to solve and visualize these types of problems. And just a reminder, there are lots of valuable resources on the TI website. There's material there involving technology and calculus, classroom activities, and lots of calculator tips and tricks for test success.